Welcome back to another day of Math 8. Today we're working on Unit 1, Lesson 12. We're continuing our understanding and continue to improve our knowledge of what congruent means. In this case, we've asked ourselves in the last lesson, are they the same? But we needed to have a little bit clearer direction on what the same actually means. When we talk about figures being congruent, we can always prove congruence using rigid transformation. We always prove that, or the reason why rigid transformation works is because under rigid transformation, we preserve or we keep the same all the lengths of the corresponding segments. Not only that, we also keep each of the corresponding angles equal in measure. So we can see that the figure, when we translate, rotate, or reflect, or any sequence of those, the shape itself never ever changes in its appearance. It just changes its location. And we see that all the sides are always maintained the exact same length, all the angles are maintained the same length, and also in the same order which the figure was first constructed. Down below here, just a quick exercise. One of the things that can help us out when we're talking about congruence, we have to understand that congruence can be proven in a number of ways, particularly through rigid transformation. In this case, we're only looking for triangles that have been translated from figure ABC. Just a quick recap, translation only occurs when a when a figure is slid or translated across a plane without turning or reflecting or anything else. The orientation has to stay the same. So that means we're only looking for triangles that look just like A, B, and C. Now I will tell you all these triangles here, they are equal to the one that's been given, but many of them have been reflected and rotated and translated across the plane. It's our job to be looking through here and decide which ones work for this. So as we work on this, think about moving your paper, your tracing paper, to each of these, and it has to maintain the same type of angle. So I use the words to help me figure out, am I keeping this straight with the same? No, this one doesn't work. This one doesn't work. That one works. The one above it does. And knowing what I know about how you guys have been working, I'm pretty sure that you can see the other ones that are just translations. I'm going to go ahead and color these in here. This one as well, there hasn't been any kind of rotation with it. This one as well, there hasn't been any rotation. It's pretty clear that this one's been rotated by some means. This one's been reflected. This one right here has probably been reflected and rotated, or actually probably just rotated. This one's been reflected. You get the point with it. We can see that. Our eyes are really good at it because of what we've been taught all our life to look for those patterns. We're going to take that same kind of knowledge and understanding that we have this built into us looking for patterns when we go and simply compare and decide if two figures are actually congruent. Here's a set of figures. We have quadrilateral ABCD and we have quadrilateral EFGH. The question is, are these two figures congruent or not? Remember that we can always prove congruence with rigid transformation. So what I'm going to do is take my tracing paper with one of my figures, and I'm going to decide, first off, is this figure a transformation of the original? And when I go ahead and get it to seat on here, I can see that I can map that drawing of the original directly onto my other piece, or vice versa. And I know for a fact now that these two figures have been, that they're images of each other, or perhaps this one is an image of ABCD. Since I know that, I can make the claim that these figures are congruent. So here's my claim. You'll hear me talk a lot about this throughout the year. And my evidence is going to be, we're going to go ahead and describe a transformation that takes quadrilateral here to the quadrilateral here. And we'll say that quadrilateral A, B, C, D is, let's call it, like with this one, let's go ahead and say is translated from D to E, because those are corresponding points. And then here we actually see a straight line that takes corresponding lengths along each other. We learned that a rotation of 180 degrees around a point will take two lines corresponding segments and overlap them. So we're going to say is translated from D to E And then just talked about this piece translating to corresponding points. We know that this is going to be a rotation of 180 degrees around center E. Now, I'm sure that some of you are thinking, well, Mr. Quilter, why didn't you just rotate 180 degrees around a center point? That's definitely another way that can be done. I would have to locate that center point by working on corresponding points and figuring out exactly where the intersection of those corresponding points are. But it will end up being somewhere right around here. Let's see here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it should be 5.5 units between these corresponding points. There's 5.5. I would estimate that would be the center of rotation right there, which we could clearly use. We could call that point M, whatever it may be, and we could just say that the quadrilateral was rotated 180 degrees around that center point. Let's take a look at another set of figures. And these ones right off the bat, if I ask you the question, are these two congruent? I'm willing to bet you would tell me no, Mr. Quilter. These two figures don't even look alike, and you're exactly right with that. Keep in mind that they don't look alike because there's no transformation. There's not a sequence of rigid transformation that will take one figure onto the other. And I say this figure to this figure simply because the alphabet, the way that it's listed, these letters come before here. So our claim here is that they're not congruent. And our evidence is going to be there is not a sequence of rigid motion that will map one figure to the other. And by stating to somebody that there's no sequence of rigid motion that will map that, we're implying that the lengths of the segments are not, there's no correspondence between the two. So I can't even determine which sides are supposed to correspond with which sides. And since there's no correspondence with any angles or any side lengths, there is no rigid motion. I keep calling rigid motion because that's what I've been used to in the past. Rigid transformation that would map one figure to the other. So the next few of them I'm just going to talk about. I'd like for you to look and make a decision. This next figure right here, are these two triangles congruent? Yes or no? There's a couple of things that we can look at to make that decision. We look at first the corresponding sides. These two appear to have correspondence between sides CB and FE. I also believe there's correspondence between AB and DE. And there also appears to be some correspondence between FD and AC. What I can do is I can take my patty paper, I can trace, and then I can check. But for the sake of time and the length of this lesson, I will tell you that these two figures, they are congruent to each other. Number 3, again, checking the shape, the size. The shape is exactly the same. I see that they're both octagons. But what I notice about this is corresponding sides. These sides appear to be corresponding, IJ and AB, because they're both horizontal. But I notice that AB is 2 units long, where IJ is not 2 units long. And I see a consistent pattern all the way around that this figure right here appears to be scaled smaller than the original. These two figures would not have congruence either. Again, with these figures where we see something that maybe doesn't quite make sense, we can take our patty paper or tracing paper, take the figure, and just simply bring it off and just saying, first off, is there congruence between the two? Is there correspondence between the two? And I clearly see there is yes. So I can make that claim. These two figures are congruent. But then since I'm making that claim, I have to explain how I know that this shape is congruent to the other. And what I would do with this one is I would take my figure and I would translate from point L to point U. Those 2 points have correspondence. And then I would rotate. I see that this corresponding side, LK and UT, are corresponding. Since I see this side is vertical, this side is horizontal, that tells me that there's a 90-degree rotation clockwise. And then I can describe that piece by simply saying that figure A is congruent to figure B with a translation from L to U followed by a rotation of 90 degrees clockwise around point U. I know I'm going kind of fast through this. Go ahead and feel free to pause the video, write down the thoughts, rewind it, whatever it may be. This will be the last one I'm going to show you. I have a few more examples, but for this one, it's pretty clear to see that when these two shapes, we can see that they start out like the length of the segment. If we look at a pattern here, we'll just start here at the top and we'll work our way around. So 3 units on the side here, followed by 2, 1, 1, 2, and 3. Whereas over here, we see a pattern that goes 3, 3, 1, 2, 2, 1. These patterns, as I work from the top counterclockwise, do not match each other, which is also another indication that there is no congruence here. Further, we see that the area of the two figures is not equal in measure. And this one right here, perhaps it's kind of hard to see, but this one is just an L shape, while this one over here is closer to a square. As I color these, hopefully you can tell definitely there's a great difference between the two figures. We can clearly see that these two are not congruent. Several more examples here. I'm going to go ahead and skip across. Feel free to work on those. One thing that I want to talk about here, this is on page 57. It says, are you ready for more? This is a challenge question right here. If you're ready for more, and you'd like to take something that will extend your thinking, a polygon has 8 sides. So they're telling you there's an 8-sided figure, an octagon, and these are the qualifications. 5 of those sides have a length of 1, 2 of the sides have a length of 2, and 1 of the sides, so the final 8th side, has a length of 3. All sides lie on grid lines. So they're saying you could draw this on a grid, and it's going to follow the grid lines vertical and horizontal, no diagonal lengths. It may be helpful to use graph paper when working on this problem. So they're going to say find a polygon with these properties, which means you get to draw that polygon that matches that description. And then the question is there a second polygon not congruent to the first? So the challenge with that is, can you draw another polygon with these exact same measures for the 8 sides, but one that's not congruent? So it would have to be a different shape. Give that a try. If you do that, take a picture of it, email it to me. I'd love to see what you come up with. And we're going to skip this one because it implies that I have to give you some objects. And if you'd like to play with this one, please go ahead. But we're going to skip this one for the sake of this lesson. That takes us to the end of this lesson today. What I need to do with this is look at these pieces of the summary and find out what is it that's important with this summary to be able to understand, have a full understanding of what congruence is and isn't. The first thing that I would like to look at is this, is how do we know if two figures are congruent? And well, if we copy one figure onto tracing paper and then move the paper to the copy so that it covers the other figure exactly, then we suggest that there's congruence. So that's, like it says, just a suggestion to ensure that we can prove, give solid evidence that's there. We can prove, that's a big difference there, that two figures are congruent by describing a sequence of rigid transformation. The key thing is that rigid transformation has to prove that they line up or match exactly. How do we know if something is not congruent? You know, our eyes and our brains are actually pretty darn powerful. And they're going to tell us when something just doesn't look right. Like when you look at these two figures, one is a rhombus and one is a square. These two figures, while they may have the same area, they may have the same perimeter, they don't have the same angle measures. This one has 90-degree angles and this one does not, which means there is no correspondence between the two figures. But when I show you this one, I think we know right away. You're like, wow, they look the same. And that's because we can see correspondence between points. We see this little angle and this little angle. They definitely appear the same. So then we would want to pursue and say, can I map figure A to figure B through rigid transformation? Another way that we can tell if two figures are not congruent is that we can just follow along a pattern for their perimeter and see, does the perimeter follow the same pattern? In these two figures, just by looking at it, I believe you can see that they don't. This is the pattern working our way around from the left side, working around counterclockwise. and then again from the top counterclockwise, and we can see that this figure, there's no way to see a correspondence between the two because they don't have the same side lengths. For the last part of it, if we look at a couple other polygons, such as these two, if two polygons have the same side lengths, 5, 3, 5, and 3, 5, 3, 5, and 3, but their orders can't be matched up. So you see this one goes 3, 5, 3, 5, and this one goes 3, 3, 5, 5. That's another indication that the figures cannot be congruent because even though they have the same two side lengths, they don't correspond in the same order. So the order actually matters. Now, if we look at one last thing, if two polygons have the same side lengths in the same order, say like these two right here, and we see that the corresponding angles of those two, we see angle A, and we see M, that are in the same position on the quadrilateral, but they clearly don't have the same angle measure. Even though the measures all the way around are in the same order, these don't preserve, or the angle measures haven't been preserved, which means that there's no rigid motion that can map this quadrilateral to this one. The bottom line is this: if the figures do not look alike, they're probably not congruent. You can always verify that through rigid motion. But when the figures do look alike, such as this one, there's a good chance that these could be the same size, the same shape. They could have the same length of segments on their corresponding sides. JI could very well be corresponding to PQ, but we would have to investigate further by using our patty paper or by using some other means to determine how or if figure A can map figure B exactly. I just want to let you know you're doing a great job. If you have questions with these concepts or questions about the video, please feel free to send me an email. Give me some feedback. Let me know what kinds of questions you still have. When you start doubting whether you can do this, I want you to put that out of your mind and remember that you can do this. Don't you dare give up. I hope you have a great day.